I think we should start. So hi, everyone. We are continuing with the ACRC webinar series together with the IEEE Circuits and Systems Society and the Solid State Society. And today we are honored to have Professor Alberto Sangiovanni Vincentelli from University of California, Berkeley. I can spend the entire hour on talking about Professor Sangiovanni achievements, so I won't do that. I will only say that he won many awards on his contribution to EDA, and he's also very much involved in the industry, most notably in co-founding both Synopsys and Cadence. So Alberto, thank you for joining us. The floor is yours.
Thank you very much for being here, actually virtually here, and let me just start my presentation with an outline. So I would like to do a sort of a review of what happened in the last 40 years, and in particular the birth and the growth and the maturity of EDA. And in particular, I would like to underline how important was the collaboration between industry and academia to bring this sector to be what it is today. Then I'll look at what is the future of EDA, and in particular at cyber and bio-cyber physical systems. And then I'll look at some challenges to the EDA industry to move into this new domain of cyber physical systems. And then I would like to give some opinion about artificial intelligence and the use of it in EDA and in other scientific fields. I would like to underline what, in my opinion, are myths and what is the reality of this technology. And then, if time permits, I will look into a very serious problems that is really making our life difficult and miserable, is the security problem. So without further ado, let's go to the collaboration between industry and academia. So if there is something that I learned in these many years of my activity at the University of California at Berkeley, that is slammed into the Silicon Valley ecosystem, is that there is always sort of a tension between the science and application. And there is no need to have this tension. Actually, collaboration would be the best. So this is, I do like a lot art and history. So this one is a picture that, in my opinion, depicts this tension between abstraction or science and the application. So Plato is pointing his fingers up, and Aristotle is saying, no, it is earth that matters. And so that tension between what we should do and what in practice and what we need to understand in the theory side is actually positive sometimes. And in fact, if I look at what has happened in research, especially in the research that has had most impact in the world, is this quadrant. This quadrant was called by David Stokes Pastor's quadrant. And there are two axes. One is the quest for fundamental understanding, typical of science, and the other one is consideration of use. So what do we do with our theory? What can we impact? So in the first quadrant, there is like Bohr, Niels Bohr, that was certainly interested in fundamental understanding, but it didn't have any consideration of use. On the other opposite corner, we have a situation where there is no real interest in fundamental understanding, but there is a lot of interest in getting application going. That Thomas Alva Edison is the typical case in point. Now, I believe that the best results are actually obtained by what I call use-inspired basic research. So Pasteur is a typical case in this domain. And then, of course, you don't see anybody in no interest for fundamental understanding and no consideration of use, albeit I bet that you can fill up with hundreds of thousands of people in our academic circles. I believe that EDA is just that, is use-inspired basic research. That was the origin of it. And so let me start with when I graduated. So I graduated several years ago, in 1971. And at that time, not much was going on in terms of electronics. So we were able to design chips that were really small, like 3,500 transistors. There were 92,000 instructions per second. Verifying the chip was done essentially with equipment like the one that you see in the slide. And preparing the mask was a very tedious and difficult step, sometimes done with screens and terminals, but most often by hand with ruby leaf. The cores of our computer was magnetic, and they were actually assembled by hands. And the user interface to our computing elements were actually punch cards. Now, if we look at what happened then after this moment in which we started looking how to design electronic system better and to increase the complexity of this system, I noticed that actually in science and application, there are always three stages that kind of repeat themselves. And this one I'm borrowing from a fellow philosopher, Italian philosopher that was active in 1700. And he mentioned that there are three stages in human history, and they repeat always themselves and with regularity. So the first one is the age of gods, where the senses are dominating the scene. The second is the age of heroes, where imagination takes and it's great innovation, new results, excitement. And then the last one, the last stage is the age of the man, which is actually the age of reason, where people look at what has been accomplished and they turn into being more conservative. Now, after that, there is a decaying period, and then again, the age of gods, and the age of the heroes, and the age of the men. So how does this plug in into the our story in EDA? So actually, EDA has started in 1964, so even before I went to college. And the first thing that people were interested in is in simulating electronic system. Why simulation was so important at that time? Because we realized that we couldn't go on developing very complex system with just measuring things and prototyping things. We needed a virtual domain where we could test our ideas and the like. And so that was actually simulation. So the key development was in the 60s was actually IBM. IBM at that time was way above everybody else in the development of electronic system, and in particular of computing system, as we all know, but also of integrated circuit. So IBM for a long period has been the spearhead of IC design. So key contributors in that time were the people at Yorktown Research Center, the T.J. Watson Research Center. And in parallel to that, Berkeley started working on simulation, in particular a SPICE program. Now, in elevating the level of abstraction, we go to logic simulation and testing. And again, here IBM was the key player. And then fast simulation. Now, we all know that the EDA company today make a big deal about fast simulation. But actually, in 1975, the first fast simulator was developed at AT&T, and in particular at Bell Labs. Now, in terms of the physical implementation of an electronic system, we're talking about printed circuit board. The layout for integrated circuit was basically done by hand, but people started worrying about how do I optimize the positioning of the components on a printed circuit board, and how we're going to connect them efficiently so that the performance could be elevated, and at the same time area and power was minimized. Now, the key point here to understanding from industrial point of view is that the CAD, the computer-aided design, as it was called then, was of strategic value for the electronic system industry. And because of that, there was a very strong group of CAD experts in every company that I knew. There was a very strong Japanese presence just at the time where Japan was challenging United States for dominance in the electronic industry. And the first generation CAD vendors appeared on the scene. So you had Applicon, Calma, Computer Vision, companies that many of you have never heard of. But some of us who are on the older age may remember. And these were essentially artwork editing and custom hardware workstations. The interesting thing is that all these companies were actually selling the hardware on which the algorithm and the user interface were running. So they were in some sense also computer companies. And this is a consideration that we have to keep in mind, because the next generation and the generation after that went away from this point of view. But at that time, software was given for free, and actually the hardware was what demanded the price. So these companies actually, they all disappeared, and the reason why is that it was very difficult to stay abreast of technology because of the software complexity that you needed to build tools that could be used. And the hardware evolution was continuous from the computing side. And so if you are a company that is selling equipment for doing design, to stay abreast of hardware evolution, it was a really challenging point. And then there was a very little customer loyalty due to the fact that this company were based on low, quote unquote, low technology. So it was essentially glorified word processors or shape processors. And then last but not least, the incapacity to read the market and the evolution of new technologies. By the way, Calma at some point was bought by General Electric, and they invested quite a lot on Calma, but to no avail. Calma essentially disappeared. So the age of the heroes is that when I went to Berkeley in 1975. So I was just at the beginning when circuit simulation started. And at that time, I was very much interested in theory. If I have to look at my trajectory, the key point was how I could build better algorithms to do simulation. And of course, Berkeley was the mecca of circuit simulation in academia. And I went there and I started contributing with numerical algorithm to SPICE. In fact, the last version of SPICE, in addition to Don Peterson, you see my name as well, because of his contribution on the numerical algorithms. But from 78 to 92 was a big explosion of EDA. So EDA became, electronic design automation, became one of the richest domain of both research and also industrial interest in electrical engineering and computer sciences. So we had key results in all areas of EDA in this period: verification and testing, layout and databases, physical verification, logic synthesis, you name it. And some of these topics are actually still of interest to people in academia, in industry. By the way, the largest vendors today, so Cadence and Synopsys, were founded during this period. So from the business point of view, workstation companies, hardware and software, but second generation, were Daisy, Inventor, and Valley. And they were thriving based on schematic data capture and logic simulation. But still, this combination of hardware and software was key for these companies. They were founded in 80, 81, and 81. Then the third generation CAD company started emerging. And so the third generation CAD company. So it was ECAD in 1982 that was based on design rule checking, SDA or Solomon Design Automation, that combined to ECAD to form Cadence in 1987. And I was among the founder of SDA. Silicon Compiler, Silicon Design Labs, ViewLogic, Gateway. So a large number of companies was born at that time. Now, interesting enough, you may see the name Silicon Compiler, Silicon Design Labs. Actually, based on the pioneering development at Caltech with Carver Mead, it was the dream of people during that time that we could develop compilers like computer compilers, which you enter design a high-level computer language, and then you would get at the output the actual implementation of the design. Now that was based on a transformation of different layers of abstraction, but little attention was given to optimization. And so that's the reason why Silicon Design Labs and Silicon Compilers actually disappeared from the scene, while EDA and this, while ECAD, SDA, and actually Optimal Solution thrive. Now, I have a little quiz about for you. So actually, in 1987, Optimal Solution was there, and it's still here. So what happened to that company called Optimal Solution? Well, it actually became Synopsys. So the original name of Synopsys was Optimal Solution. So you see there has been all kind of interesting developments in the industry. Acceleration companies were born. QuickTurn 1989, PyDesign 91, ICOS. And so we know that the Synopsys, Ventor, and Cadence do offer this acceleration hardware to be capable of running simulation at much faster speed, which is an essential step to develop the computing systems we know them today, cell phones, TVs, and so on and so forth. Now, there was still strong investment in internal EDA by IC companies like Intel, Motorola, TI, Infineon, Philips, and so on. So all of these companies, because of the realized that the strategic value of EDA was warranted an important investment. Now, interesting enough, the strongest competitors of the CAD companies at the beginning were actually the internal groups. Some of the companies that were not as rich as Intel, for example, or IBM or Bell Labs, started looking at vendors to download what they were doing inside of to vendors so that they could obtain the best technology without investing an arm and a leg. And IBM and Bell Labs still had the technical leadership in industry. And I would say some of the researchers in IBM and Bell Labs were definitely at the same level as what you find in industry. Company life cycle. So the second generation business model proven not to be sustainable. Due to what? To the dominance of general purpose workstations. So in 1983-84, actually some of the first Masscom was the first company to become viable for engineering workstations. And the engineering workstations were all based on Unix operating system. And in fact, the interesting twist in Cadence was just the realization that workstations and Unix operating system was going to dominate the scene. And so all the tools that we developed during that period were based on workstations and on the Unix operating system and the C language. Now, in fact, a turning point, in my opinion, at least for me, was in 1983 when Intel started developing the 386. And that was 275,000 transistors. Now, the picture that you see here, one was Gene Hill was the manager for the design. And then you see Pat Gelsinger, now is the CEO of VMware, who was the chief technical officer for the 386. And the one with the bow tie, as I have today, is me. many years ago. And what you see there, it was a presentation that was recorded and then distributed to all universities at that time, that explain how we could use tools to conquer the complexity of the design of the 386. That, remember, only a few years ago, we were able to do 3,000 transistors on a chip. Now we have 275,000 transistors, so 2 orders of magnitude bigger. And many people believe inside Intel that they were never going to make it. And so they came, actually, Intel, and in particular, Albert Yu was the head of all the microprocessor division of Intel, came by and said, well, look, you have to help us, you Berkeley, with your new tools, because otherwise we'll never be able to do it. And so that was the big luck in my personal career, because indeed we were able to design a 386 in time, and was the first time that automatic placer route and logic synthesis was used for the design of the vendor chip. And in fact, if you look at the evolution of the microprocessor, Intel microprocessor, you see that from the 4004 to the 8086 to the 8286, there has been a very clear pattern. So from very confused design, if you like, so a lot of spaghetti thrown on the floor, you see that you are marching towards regularity. And regularity is a way of conquering complexity because it's easier to manage complexity. And in fact, the 386 was an exemplary towards that direction. And in fact, you can see that there is no more spaghetti thrown on the floor. And the key idea here was to use libraries of cells. So it was the first time that standard cell design, that was actually proposed by Bell Labs several years before, was used for a microprocessor design for the logic part of it. And so regularity, libraries, and tools were the key to make sure that this chip could make it to the market. Now, notice that this was not easy to push through because several designers were afraid that using libraries, regularities, and automatic tools were not giving the level of optimization that they felt was needed. So it was a serious fight. And one way of convincing them was actually that we could get the same result or better results in a fraction of the time. So only by showing that we were able to get the attention of designers. Remember the design compiler story. And the design compiler never made it just because the quality of the design in terms of performance and area occupied was not comparable to human design. And so optimization, and if you like me to tell theory and algorithms were key in order to start the EDA industry. So how did we cope actually with complexity? So this is sort of a distillation that I got a few years ago just by looking back and say, what did we actually do? And then the key point was the introduction of abstractions, and abstractions are a way in which you try to eliminate details that don't matter, and you focus on what really matters at one level of your design. So when you do physical layout, what matters is the geometrical shape. When you do simulation, is the ordinary differential equation. They describe the circuit. When you start doing the logic design, what matters is the operation of a transistor, not its characteristics. And when you go up and try to form an architecture for your chip, then you're talking about computer languages that are used to describe that entity. So abstractions was key in order to conquer complexity. But mind you, the important point in introducing abstractions in design is always trying to find what is the level relationship. So if you are a high level of abstraction, you always have to realize that what you do here has an impact on the implementation level, but this impact can be estimated at the higher level of abstraction, so that when you finally go to the implementation, you have no surprises. And because of the use of abstraction, then you can use tools. But the most important thing, in my opinion, is actually methodologies. And we call methodologies freedom from choice. So if you look at what a methodology is, it's a set of rules that have to be given to people who do designs so that they don't get into corners that are very difficult to analyze or very difficult to assess properties of. And so it's so important that people follow methodologies. And I guess many of you who are a circuit designer know what I'm talking about. And in particular, in the methodologies sector, we insisted that synchronous design were considered. Otherwise, you couldn't do synthesis at that time. And so that limitation, together with the limitation of using standard cells, for example, for the layout, were critical in conquering the complexity of the 386. Now, at this point, after we did all this analysis and we developed algorithms and we were able to demonstrate with 386 that actually EDA was feasible, then it was time to offload the ball. So from academia to industry in a major way. And so here we go to the companies I know best, Cadence and Synopsys, that were really a step from academia to industry. It was a typical case, if you like, of technology transfer. I hate the term technology transfer because you don't transfer technology. You transfer ideas, you transfer people, you transfer approaches, but technology is not like you develop something and you throw it over the wall and you say, catch it and run with it. That's not the case. You have to prepare the new developments by participating into it. So Cadence was founded in 1983, as we said, and the key ideas were the following: open database. So we started saying a proprietary database for IC design was not going to win. Unix workstation, for the reason we were saying before, simulation and automatic layout. These were the basic tenet of what SDA and ECAD started working on. There was a new funding model. At that time, Silicon Valley was still not very well developed. Yes, was growing, and it was mostly silicon companies, and a few computer companies were surfacing. But the main way in which you would fund a company were venture capital. But for this particular case, we went to a mixed funding model where companies that were using the technology would pitch in as much money as this is actually more, because we got 4 million from companies that were interested in the technology and 1 million from VC. So we actually went public in 1988, and this is an interesting story because we were supposed to go public in 1987, unfortunately on Black Monday. That was the day in which the stock market had the largest drop in its history. And so we had to withdraw the IPO, the initial public offering. But since we did all the work to get ready to be quoted on the stock market, we did what is called a reverse merging with ECAD that actually was born together with SDA. We were always supposed to get together, but ECAD was able to go public before the Black Monday. And so our only way is to combine the two companies. And if we look at the history of Cadence, as of today, the market cap is 31 billion US dollars. So considering that there were 3 of us funding it in a restaurant at Berkeley, was quite an accomplishment. Now, another interesting thing is that, coming back to the Intel story that I forgot to mention, which is very much related to Israel, was that at that time, Intel opened a, a location in Israel. And in fact, I see some of my old friends like Avi Kolodnik participated to that adventure in 1983 for the 386. So Intel put together a group of 20 people or so to get educated, if you like, in CAD or EDA, and then was the seed for the design technology group at Intel that at its heyday had more than 1,000 people. Now, and by the way, Cadence has touched its top value just 2 weeks ago. So continued growing. Same thing for Synopsys. Was founded in 1987. Was based actually on automatic synthesis. So at the beginning, the two companies were separated. They didn't have overlapping. We use the same funding model of Cadence, of course. Went public in 1991. We didn't need to do reverse merging. And as of today, is $32.78 billion US dollars. So the sum of it was about, well, $64 billion, which is really, at least in my view, impressive again, considering where we started and how much time has gone by. And while the first generation EDA company and the second generation EDA companies disappeared, Cadence and Synopsys stayed alive for all this period. Now, if we look at the impact of this of EDA, we can see that logarithmic curve that you see here that it indicates how complexity grew in going from 1970 to 2020. That the role of Cadence and Synopsys was absolutely crucial. Now, the interesting thing is that we are hitting the wall on the capability of putting transistor on a chip. People think that 10 billion is about as big of a chip as you can make. Probably you can go up with respect to that, but not by much. So now, the key point that I want to stress also for academics is that often and industry as well. Now, when we talk about design, people think about practice, right? So I want to get to the result as quickly as possible, and I want to be able to hit the market as quickly as possible. So sometimes people say design practice is what matters, but I think that practice yields this kind of structures like Palafit. Like these guys can last maybe 3 years, 4 years, 5 years, but then they collapse. Now, what I strongly believe is that what we have to do and what we have to base our work is about design science. And so we have to teach principles, not techniques. And actually, there has been an evolution also in the classes in IC design at Berkeley, so that principles are more the matter of the teaching activity more than the actual techniques that are, of course, needed for building a circuit, but it's most important to press for principles. So this one is actually a Greek temple that was built in Sicily 420 years before Christ, and still there, right? So that's the reason why I think we should go based on principle, not techniques. Now, what are the general principles of electronic design estimation? So, well, there are two processes that I call vertical and abstraction and refinement principle. One is what is called verification. Verification is in the vertical is when you move to abstracted level. And the verification complexity is managed by abstraction. So you reduce the number of items by aggregating objects and by eliminating unnecessary details. And decomposition. So you have a large system and you divided it up into pieces so that you can verify in a better way. So abstraction is in some sense is a vertical step, while decomposition is an horizontal step. It's something that you act at the same level of abstraction to simplify the task at hand. Now, there is another important issue about designing. And so design complexity is actually managed by construction. That was the lesson that I learned when we developed logic synthesis together with Bob Brayton. And that is a refinement, which is you start high in the abstraction layers and you map this higher level in a lower level. And composition, that you assemble a design by composing existing parts. So design reuse, if you like, is an important concept here. So if you look at what we do by design, we do abstraction and refinement on the vertical sense, and composition and decomposition at the horizontal layer. And no matter what you do, if you are going to use any design methodology, you can find these two basic concepts, horizontal and vertical. So the vertical, abstraction, refinement, abstraction moving up, refinement moving down, decomposition, breaking, composition, assembly. So in fact, these principles yielded what we do today to design chips. Is essentially the system on chip paradigm, is that you assemble very complex chip by picking up things that have been designed before. And so you assemble components for parameterized library, and you include configurable processor core, memories, special purpose standard blocks, and then you have a glue logic. And then you can assemble third-party special purpose logic like MEMS and others and other components. You integrate using standard approach to on-chip communication. And that is what is the key to build some of the chips that we are seeing today in the world, is this composition of existing parts, the design reuse, and assembly of parts. So if you look around, some of the most complex chips that have been designed today are from Apple, Microsoft, Amazon, Google. So there are system companies that became circuit designer because the design methodology has evolved so that it can be done. So in some sense, this idea of assembling components and putting them together to yield a more complex system is making a sort of mass production, because you have all these units that you have been able to develop and optimize. Think about an ARM core. But you can assemble in many different ways. So it's essentially a mass production of the components, but assembling the components, you actually do a single design. So by doing that, you can bring to market much more designs that you were able to do before. The automotive industry has gone that way with the so-called platform approach. And actually, many of my papers talk about platform-based design, in which you develop the components of an automobile with great details, but then you assemble it very quickly so that you can build a new model in a year or a year and a half, while before, to bring a car to the market, you need at least 5 years. So I was talking about the largest chips being designed by system companies. And in fact, here is the Apple A11, which is actually 4.3 billion transistors. So we are really getting there. We're really getting to the 10 billion transistor that I was talking about before. And I know some developments now that are hitting that particular level. And if you look at the layout, it's very regular. It's composed of pieces, and it's based on this assembly of different components. So now, when you put together the various parts, a key point of the design is about composition. So people like to say plug and play, but very often, if you are not very careful about the principle that I was saying before, you're actually doing plug and play. So you plug things together and you hope that things are going to work. And a rigorous methodology about interfaces and how you combine various pieces is essential to do real plug and play and not plug and pray. So actually, the key point in doing plug and play and not plug and pray is a formalization. So how you formalize the design task that you are developing. And so again, my love for art is shown here. This is my favorite painter is Renaissance painter, Italian Renaissance painter is it's called Piero della Francesca. And you see, for example, on the picture on the left is the absolute symmetry of the design of this wonderful piece of art, where everything is actually studied to perfection. And on the right, you see the principle of abstraction, because everything is based on the study of perspective. And even the flagellation of Christ is as a abstracted view. So it doesn't even look like a flagellation. So formalization keys. Virtual design and refinement, as we mentioned earlier, is a key component. This is Michelangelo, the Sistine Chapel, and you can see the successive refinement that yielded all the parts of the Sistine Chapel, from the schematic capture down to the actual implementation of the painting. And last but not least is library-based design. Here, this one is the Capitol in Rome. It's one of the most wonderful squares in the world. And what you can see is that there is an interesting aspect to this design. You see the statues that are sitting, the two Castor and Pollux with the horses. Actually, this was a Greek statue, and Michelangelo actually broke the statue up and it put it in that position because, in his opinion, was giving a wonderful feeling to that square. Now you may see the horseman in the middle of the square, and that it was Marco Aurelius, and the statue was Roman time. And again, Michelangelo took it and positioned it in the center of the square. Last but not least, you see on the corner, up right corner, you see the design of the actual square, and that design is identical to what you can see in St. Peter's Square. So Michelangelo was using that pattern to give a particular feeling to squares, and he kept on reusing the same. And so in the libraries were statues that were found in Rome because of the history of Rome and of his own interpretation. So what kind of business challenges do we have today in EDA? So the first thing is that we must adapt to changing business conditions and structures. We also have to see that client-vendor relationship have changed a lot. So it's much more a partnership than it was before. So you have to work with your customers. And also the technology is really challenging, it's really changing. But last but most importantly is that we must extend to other fields to keep alive. And that is a key point that I wanted to stress, is the importance of extending the reach of electronic design automation to other fields. And in particular, we have seen in the past 10 years, 15 years, the emergence and the key attention from industry as well as academia on cyber physical systems. So, and bio-cyber physical systems. So what are these systems? So cyber physical systems are interconnecting the world around us and make it smarter. This is the key tenets. And so we can think about the modern rendition of an airplane, of a car, of buildings, of power generation distribution, factory automation. In all of these domains, you see the digitalization taking place. And the digitalization is adding a dimension to the physical designs, like, for example, wind mills, the buildings, the car itself. In fact, many people think that car today is essentially a shell to an electronic product. And you can see that, in fact, Tesla success is basically about that motion from the mechanical domain towards the electronic domain. Now, but there is also another important dimension, is that is the linking of the biosystems to the cyber system. Biosystem, what are they? Essentially humans. And how do you connect the cyber and the biological world? Well, there are plenty of companies and research papers and conferences that are now more and more involved into the coupling of electronics and our physical dimensions, and in particular the connection from the brain to the internet, the connection from the brain to artificial limbs are key elements. In fact, Elon Musk has just started a company a couple of years ago that is trying to develop this technology and made it available to the world. Now, of course, there is a lot to be careful about here, because you can imagine how security can come into the picture, in the sense that people may be hacked. So, and as long as a computer is hacked, is not a life or death problem for most cases. But in the case that you are connected personally with your brain to the internet, being hacked is a question of life and death. So we're still quite far away from getting a reasonable connectivity between our physical being and the infrastructure, but it may come, and may come earlier than we suspect. Now, the prediction that we have put together for the past 5 or 6 years is about the fact that the future is going to be about sensor actuators that are widely distributed. And so there is no more the focus of electronics, no more the cell phone or the laptop. Is going to be the environment. The environment is going to react to ourselves. The environment is going to be the computing engine. It's going to be what is allowing us, enabling us to develop new business models, a new way of living. And in fact, several market studies say that by 2025, we'll have 7 trillion devices, which for 7 billion persons, so will be 1,000 devices per person. And actually, it's not that we will carry 1,000 devices on us. It's just that these devices will be distributed everywhere. And so, for example, we can imagine being immersed into a space where we can interact with other people remotely in a much better way than we are doing today. So they could really have the feeling of having a conference in a real environment. And with we can imagine of controlling screens and moving objects on the screen with simple gesture, and already some of these applications have appeared. But more interestingly, and is a research that we're carrying out in these days, is the use of technology to fight pandemics like what we are witnessing now. There are several interesting applications being developed that actually use electronics to quote unquote kill the virus and sanitize environments. But stay tuned. This is new developments that are coming down the pipe. So how safe is our design today? We have seen that all this interaction between different components, cars, humans, all connected together. Now, what is the confidence that we may have in our design? So I hope that is more on what we see in this a nice picture that was taken at the time of the development of the skyscraper in New York. And so, in fact, the CPS problem poses much larger challenges than what we have witnessed in electronic design automation. Why? Because we have this multi-physics domain. We have chemical entities. We have mechanical subsystem. We have a hydraulic subsystem. And we have the intelligence that goes in it. And so we have to be careful about orchestrating all these components such a way that they cooperate to yield a function that we need. Now, you say, well, what is new? We were able to design, we were designing controllers, engine controllers for automobiles since 40 years ago. So what is new here is the co-design aspect. It's the fact that the physical system, so a mechanical system, can be designed keeping in mind the fact that there is going to be a computer and algorithms that are going to act on it. Think about fighter planes. Fighter planes are essentially unstable systems, and they are stabilized by control. And if we didn't have this convergence between different domains, we could never design a plane of that complexity. There is also a mathematical issue here because you have a mix of different notion of times. You have untimed domains, you have discrete time, you have continuous time, and you have to put them together because the various parts are interacting. And so what does it mean to interface a finite state machine with a continuous time system? The mathematics are disjoint, are incompatible. So how are we going to make them work together? So again, the problem is managing dynamics, time, and concurrency in a very complex domain, which is network, distributed, computational, and physical system. So to give you a simple example of what a cyber physical system look like from a design point of view, we have a system which is actually a robotic arm. And to describe the motion of this robotic arm, we use an equation-based model, mostly based on partial differential equation and ordinary differential equation. And the abstraction is a physical model of the actual mechanical motion. On the other side that you see is the electronic subsystem that controls the motion of this robot, and which is carried out by an embedded system, which is plugged into the body of the robots, which is made of sensor network of computing elements and actuators that send commands back to the physical system. Now, the abstraction here in the embedded system domain are all based on the different concept of time. And so that particular aspect is what we call a model of computation. So how we are going to represent the operation of the cyber system and what kind of mathematics we should use to do that. Now, what are the modeling challenges for CPS? Well, is what we learn and what we know how to do in computer science is relevant, but is not actually enough to yield what we have to solve when we think about cyber physical systems. So we have to have physical model-based computing and resource-aware, so which means time and energy composition. So we need to have a formal way of composing multiple physics, and then we have to be made sure that whatever we do at the software and algorithmic level is cognizant of what may happen in the actual physical domain. So let's look then at how CPS system and computational software come together. So the problem of analyzing this system that we outlined before lies into the algorithms that we use to simulate this system. So it's the solvers. And one of the big problems about this combined continuous and discrete system is just the complexity that we have to manage in terms of simulation and composition of different mathematical domains. So in particular, when we are designing, for example, fluidodynamic system, even microfluidodynamic system, we have to deal with partial differential equation. And so the frontier is about the underlying math that we have to do to bring to market new simulation tools that can manage the extreme complexity of multi-physics. And so the numerical finite element method is the numerical method of choice for solving PDS. And in general, we PDE is actually partial differential equation. We discretize PDEs into meshes, and then the PDEs become linear sparse matrix to solve. And so the performance and capacity of this finite element method solver is largely reduced to solving a large number of matrix equations. But it's interesting, and this one is something that I would like to impress about the validity of the long-term thinking. So today, the distributed matrix solver that is used in Cadence solvers are based on the idea of having a leaf of the system, so the component of the large matrix as being sparse matrices, and then a root that is the composition of this sparse system, which is actually a dense matrix. And so this is essentially the way in which the distributed matrix solver looks like. For every subsystem in your cyber-physical system, you have a matrix that describes it. And so these are the matrices that appear on the main diagonal. And then you have the borders that describe the connectivity of this component. So P1, P2, P3, P4 here are the connectivity parts. So now the interesting point is that the method for solving this equation goes back to a paper that that is related to the computation, the Sherman-Morrison-Woodbury formula that I wrote with a colleague of mine in Italy that has its root in my thesis in 1971. So we are talking about things that are prehistoric. But yet, these algorithms all of a sudden find their application in a very modern problem. And so the issue here is that if you really look at principles, they are going to last for a long time. And so don't give up if you develop an algorithm and say, oh, it's too early, nobody's going to use it. Sooner rather than later, someone is going to pick it up, hopefully. So now let's go to the, probably given the time, is the last part of my presentation, which is about the issue of artificial intelligence and how artificial intelligence is making its foray even in EDA. So, well, the most impressive application of AI, in my opinion, is in autonomous and semi-autonomous vehicles, which is indeed a very vibrant, novel development in the automotive domain. And actually, if you look at the very quick development of this field, we went from 7 miles that were driven in automatic mode in the 2004 Darba Grand Challenge to the 10 million plus miles driven by Google's autonomous car. And the importance of autonomous driving, in my view, is not only the fact that it is more efficient and so on, but it's the safety aspect. So if and when we are going to have an automotive system completely unmanned, then we're going to save millions of lives. So what are the 4 fundamental questions of autonomous driving? Where am I? And so this one is sensing technology and a standard, standard quote unquote, that is semiconductor based. What is around me? And so these are vision systems, radars, lidars, camera systems. And here you using machine learning to recognize the images that this system collect. And a very important development in this domain was Mobileye, the Israeli company that has been acquired by Intel. Is really a great story about innovation in this domain. Now, what will happen next? So once I know what is around me, what will happen next? And so predictive systems. And so I need to solve differential equation and the like to understand the motion of the cars. And then the last but not least is what should I do? Given what will happen next, what I'm going to do. And these are decision systems. And they are based on machine learning, connected cars, and trip planning. So the key point here is sensor fusion and AI and machine learning. But if indeed the decision system is based on machine learning and AI, what kind of confidence can we have in this algorithm not to kill people and not to create more problems when they solve? And so actually the enabling technology we said before of many things is machine learning and artificial intelligence. But why is that the case? Well, there is a very important issue to underline, is the enormous amount of data that is created. So we're talking about terabytes, thousands of terabytes of data created every minute. So there is a humongous number of data that are created from our standard, mainframe and internet, mobile, social, big data, and the cloud, but also by the Internet of Things. So if we have the famous embedded human, so for embedded human, the number of 7 trillion devices, you can imagine the amount of data that is created. So the key driver for the use of machine learning, and many people tend to confuse machine learning with AI, is the data. So big data plus processing power is the new age for artificial intelligence. Because having big data is not enough. You have to have a lot of processing power to make sense out of the big data. And to make sense out of the big data, you have to find a way of extracting meaningful information from this big data. And so how are we going to do that? Well, look, the fame of the intelligence of artificial intelligence is about the application that we're seeing that are really impressive, that are essentially gaming, right? So we know that recently AlphaGo has beat Lee Sedol, that is the world champion of Go, which actually is one of the most complicated games known to man. And so the fact that you can beat a human at a very intelligent, quote unquote, game was really impressive. But is that really a demonstration of what we can do with AI, for example, in autonomous driving? The games are characterized by fixed rules. The environment is well known. So the thing that you use a machine learning for is to dominate complexity and to try to figure out what you can do based on a precise environment and framework. And in fact, the Michael Jordan, a friend of mine and dear colleague at Berkeley, says that really imagining that machine learning and artificial neural network mimic the action of the brain is a delusion. So it's not the way it works, not in the least. So you have to think about the mathematics that is behind neural network and machine learning. And just because these methods are based on empirical data, it's fairly easy to fool them. And so I wouldn't trust my life on a driving car with, whose logic is based on this principle. So what you see here, for example, up corner to the left, and this is a paper from Stanford, they were able to make a AI software classify that strange blob as a king penguin. Now, if you look at the left, that's the real king penguin. And on the bottom right, you have a meaningless picture with a particular color pattern. And the same AI has declared that to be an African gray, which is the parakeet that you see on the right. Not very similar indeed. And the point is that these algorithms are extremely fragile in some sense. So they do well on what they saw. They may not do well in something they have not seen before, they've not been trained for. And so the bottom line actually is that machine learning is a glorified statistical inference. So you're looking at data, you're trying to approximate this data with a function that explains this data, that regenerates this data if given the appropriate input, but is based on analyzing what you have seen. And so it's an extraction, so it's an inference. And so as any inference is prone to instability. So think about solving ordinary differential equations. Explicit methods are inferences, and explicit methods tend to be unstable. And so you have to realize what machine learning can do for you. So for certain applications, they're just fine. For others, they are not, until we develop a new understanding of what kind of algorithm we need to solve this problem. As I said, security problem, I was almost sure I was not going to have the time to do it, so we'll just go to my conclusion, final words of wisdom. So now, one thing that I would like to stress again is the value of innovation. So all this history of EDA, of the introduction of new algorithms and so on, are related to the understanding of what is innovation. And I believe that innovation is essentially an innovative ecosystem is like the Amazon forest. And I would say that Israel is a typical example, as well as the Silicon Valley. Is in fact the presence of large companies, think of Intel, IBM, and so on, as well as small startups, and you have plenty of them, together with first-class universities. And so, in fact, universities are indeed an important part of the equation. So in Silicon Valley, you have Stanford and Berkeley, in Israel, for sure, Technion, and other Hebrew University, and so on. And so you have the same pattern that is developing over and over again. And in my opinion, there is also another important part of innovation, that is the capability of recognizing where innovation is. So I equate innovation as truffles. Now, I do love to cook, and truffles are really fantastic food, but are very difficult to find. You cannot grow them. You have to create the ecosystem where they can grow. And the white truffle can only grow in a particular, very particular ecosystem. And this ecosystem is the Alba region in Italy. In order to find it is extremely difficult, and you need specialized animals like a dog, like a truffle dog, which is trained to find that. And my view is that we do need truffle dogs to find innovation where it is. And so venture capitalists, government, and so on, they cannot make innovation happen. They can discover innovation where it is. They can make it happen by creating the best condition, but not by a top-down action on topics, on person, and so on. They have to create the ecosystem. And so, in fact, the relationship between the ecosystems and the importance of the investment in this ecosystem is explained by this diagram here. This one is the H-index of patents. And you see that the highest H-index for patents is Silicon Valley. The second highest, this is in the United States. The second highest is in Boston. If you look at the investment volume, they are exactly in the same proportion as these two peaks. So, which means that the capability of innovation is creating the economics that are so important today. Now, so in summary, my last two slides, innovation is essential for a new normal. And in particular, you know, we are witnessing a very critical situation today. All companies are suffering, and a way of getting out of that suffering is to use innovation. Now, innovation exists through research. It's not equivalent to research, but it has its roots in research. Another important issue is that if we look at the companies that have thrived, even thrived in this very difficult period, are the ones that have been able to quickly deploy digital technology and similar approaches. And in particular, there is a say that in this last 6 months that we have suffered through, the acceleration towards a digital world has been equivalent to 10 years of development. So 6 months, 10 years. So we are really on the boundary of a new way of living and working. So collaboration between industry and academia is essential, in my opinion. Plenty of very serious problems to face. Computational software, of course, you know, that was my first foray into research. So computation is very important. Computational software is very important, but beware of fads. And there are plenty of fads around. And so we have to make sure that we are not swindled by the how to say, enthusiasm about new technologies that are not necessarily the best technology to use in a given environment. So it has been a long and wonderful journey. So it's been more than 40 years for me in this domain. It's not over yet, and there is a lot of stuff that we can do and needs to be done. In other domains, maybe in electronic, we have reached sort of a plateau. We are doing better and better, but it's still a new version of what we know how to do. Principle must guide our research and teaching, not techniques, but principle. We need new paradigms to go beyond what we know. Embedded systems, cyber physical systems, system of systems, and so on. Molecular electronics, synthetic biology, and, for example, even make our foray in building. And last but not least, I think, education. So we have seen, unfortunately, in the latest events in the United States, that education is not really there worldwide. So people believe in fables and in stories and not in science. So one of our goals as educators and as men of science is to also to make people appreciate what a real result is based on facts and based on understanding of the underlying mechanism and not on things that have been word of mouth or hardly reasoned upon. So thank you very much for your attention, and I would be more than glad to answer any question you may have.
So for questions, just raise your hand or write in the chat and we'll unmute you.
Can I ask orally or I have to write in the chat?
You can start.
I can try. Okay, my question, Professor, is what are your predictions for future? What the future will behold? What's new technologies?
Yeah, well, for one thing, I definitely think that the most important future is indeed in the biological world. And the recent Nobel Prize given to CRISPR-Cas9 is opening an entire new vista on curing diseases and creating a totally different science as what we have today. The good aspect of it is that, as in synthetic biology, the role of algorithm and even EDA in these domains is going to be a non-minor role. So that's a good sign for us. Now, in terms of other domains, it's obvious that if indeed we can master the art of designing quantum computers, then that is another breakthrough technology. And then I also like to think that the combination of technologies like microwave and UV and inference like artificial intelligence in fighting these horrible diseases that are going to come towards us. So we have seen the last pandemic, COVID-19, but it's not going to be the last. Something else is going to come down the pike. And so the future is about using technology and more effective tools to fight this pandemic. So biology, medicine, and quantum computing, in my opinion, are very important for the future. You may say also AI, but that is more a thing of a present, and I actually predict that there is going to be a sort of rephrasing artificial intelligence in its correct boundaries.
Thanks for your answer.
Okay, other questions? Are there other questions? Jacob.
The question in the chat.
Yeah, I'm looking at the chat, in fact.
There's a question from Gadi, yes.
Yeah.
You mentioned that 10 billion transistors are the limit. How do you estimate it will be broken?
Well, I mean, it's interesting because, in my opinion, it will be broken not so much by the technology itself, but by the design aspect. Meaning, instead of thinking about 10 billion single chip, think about 100 billion with chiplets. And chiplets, if you look at what I've shown as system on chip design methodology. Now imagine that each of these components are actual pieces of silicon, and then you are going to combine them together, 3D IC packages, for example, or even combining them in novel ways. So in my opinion, that is the way in which we are breaking the barrier of the 10 billion transistor electronic system.
Just to follow up that question, so basically from the design point of view, each chip will be designed in the conventional way, but the total number of transistors will be higher, right?
Will be higher, but because it's not a single chip, it's going to be multiple chips.
Exactly, but so every chip individually will be limited to the 10 billion.
Yes, correct. But they think about the system, right? And look at the technology to be able to put these 10 billion chips together in close quarters and to obtain the performance that we may obtain with a larger chip.
Okay.
So in fact, yeah, I see you haven't mentioned quantum computing. I actually mentioned it in the answer of my previous question. So yes, you know, quantum computing, in my opinion, is still far away from being practical. I think that at least 5-6 years. But you know, I was a bit skeptical about the you know, the technology itself. It's not so much quantum computing. You know, the algorithms and the like are very exciting. Quantum gates is really very interesting. The quantum rules of putting together quantum gates is really a new domain for electronic design automation and algorithms. What I'm more skeptical is about the physical implementation of the quantum computing. But I believe that there are some approaches that are being developed that make myself a bit less skeptical, actually a lot less skeptical, so much so that I just accepted to become the chairman of the board of a quantum computing company, quantum chip company, and that is called Quantum Motion, and it's a UK-based company that came from the research done at Oxford and UCL. And my view, and it's also their view, is that the way in which we are going to bring quantum computing to be relevant is to use silicon technology. And so they have a very interesting approach to build quantum computers on silicon technology. And so that's what I see in the quantum computing domain. Now, if indeed this company can realize a readable chip, I would say a chip that contains, I mean, in principle, we could build a chip that has the equivalent of 1 million quantum qubits, right? Quantum bits. Now, once you have 1 million quantum bits, you can do a whole lot of things. And so that's, in my opinion, what the interesting challenge are. How you use silicon technology to build this kind of new computers. So, okay. You were stressing the importance of efficient computation. It seems that recently database management becomes even more important challenge. Yes, of course. I mean, when I think about computation, I also think about the not only the algorithmic side, but everything that has to do with computation. And if you like, I see that the database organization is part of the algorithm for computing. So for me, efficient computation does include the database management system that underlies it. Now, if you think about database management in terms of organizing the data, for example, for, I don't know, for marketing purposes or for airline scheduling, things of that sort, then indeed is the most important part is to organize the data in such a way that can be accessed very quickly. The algorithm itself is simple, but the key point is how this simple algorithm can get access to the data quickly and reliably. So definitely database management does become a crucial element.
There was another question about the 10 billion transistor limit. Why did you choose this number, and what is the limit?
Oh, 10 billion is just, yeah. So I chose that number. It's just a round number, so it looks good. And also, I saw how difficult it was to design a 4 billion transistor chip. And last but not least, this was discussed with my friend at Intel and previous friends at Intel, in particular Pat Gelsinger. We had a long conversation about the wall, right? The 10 billion transistor wall. But mind you, sometimes is also the issue of getting sufficient yield, because if we assume that we can go to 1 nanometer, then 10 billion is feasible, and probably even a bit more. In fact, I did say it's likely that we may go a little bit more, but we're close to the limit.
Okay, other question?
Yes, I have a question or comment. One is regarding the huge amounts of data that you mentioned that are generated. I think the biggest challenge is to learn to ignore most of it that is really both useless and definitely unrelated to each other.
Yes, totally.
We have sometimes aggregation that's a simple tree relationship that's easy, but generally the fact that I took a picture in Israel and you took some picture in wherever you are, and someone drove a car, bought a Coke somewhere, is really unrelated. So you can create a huge matrix and claim that everything is related and look for things and not find them. But getting rid of it is, I think, really the main thing. The other thing regarding what you just mentioned about numbers of transistors and yield, I think one of the challenges is to learn how to put the fact that we don't really need perfection, to bring it to bear and relax the requirements. Because with pure digital, we don't know how to handle this. A single bit flip can in principle destroy everything, but it shouldn't be that way. I mean, in the real world, it's not like that.
Absolutely, totally agree. But you see, the point is that, okay, so let me comment, because are all very interesting things. So first of all, huge amount of data. What do you make out of it? You know, the key point it did is abstraction. So abstraction is getting rid of things that are totally irrelevant. I wouldn't say unrelated. I would say irrelevant. Because you may say that if you take a picture in Jerusalem and a picture in South Africa, they may be related by what? For example, by the use of the technology. So did you use a cell phone or did you use a camera? And that information may be very useful for someone, for example, for the manufacturers of cell phones and cameras. So they are apparently unrelated, but if you look at from a particular angle, they are related.
It's an aggregation relationship, not a true dependence.
No, not dependence at all. No, totally agree.
Yeah,
but the
aggregation is relatively simple.
No question about it. And that is my point is about inference, right? Because what often these AI approaches are correlation, not causation. And correlation means, well, there is something that looks similar, but is there a reason why, right? And sometimes you don't find the reason why, right? So, and that is the problem. So correlation is not causation. And so if you actually use that as a, I mean, you use correlation and you mistakenly take it as a causation, you may take the wrong, totally wrong conclusion. Just to, and also, you know, this yields the fact, yields all the problems with bias of data and all of that. So for example, if you, when I give a lecture in presence, right, and I look at the audience and I see, for example, that there are more bald men than men with hair, I say, well, it means that people that are interested in science are bolder than are bald, right? Which is totally not true, right? But is given by the fact that my universe of observation is what I see then and there, and that is limited. So how do we make sure that the relevant information are given to prevent bias, but also how do we make sure that the damn thing doesn't do causation by correlation? And that is, you know, it's a real problem in my view. But also I have some hope that we will be able to do automatic abstractions so that to get rid of the irrelevant items. And by doing that, it's like what we do in EDA, right? So can we do that? And can we apply something like that to big data? And again, sometimes people confuse big data with AI. That doesn't have to be. So you may do big data with other algorithms than AI, machine learning. You can imagine other way of extracting information. We don't have them yet to the point that we can say we can challenge neural network based machine learning, but sooner rather than later something will happen. So I see a question is saying, what are your thoughts on security and safety factors and the growing complexity and spectrum? So the security aspect are really damning. I mean, it's just mind-boggling. So we do have some approaches that I think are interesting, and I personally very much interested in what we call bare metal security. So trying to enforce security at the transistor level, at the chip level, so that you can realize if you have been hacked at the lowest possible level of abstraction, because that cannot be fooled. So let's see what we can extract from knowing the actual behavior of registers and memory transfer and all of that on the attack. But in my opinion, security is going to be the cancer of modern, of the future society, meaning that we may see things that are really impacting the entire world in not a positive way. So we already seen, you know, fake news and all that, but we also saw the incapacitation of energy generation plant. We have seen the attack on hospitals. I am just waiting for an attack on cars, and they are very vulnerable, by the way, trains, and you name it. So it is, we are entering into a very dangerous situation. So do I have a solution? No, I don't. But the first thing that we have to do is to observe what is going on and realize if you are being attacked. That's the first step. And then there are going to be, and this is a technology that we need to perfect, is the realization I am under attack. And then the patches to that I am under attack is the second step. But first of all, let's figure out what is in there. Now, the safety factors is, as we said before, if we have a humongous amount of data, but that humongous amount of data may mislead us. And that humongous amount of data may not depict all the possible conditions upon which I have to make a decision. So think about automobiles again and autonomous driving. So if the car finds itself in a situation that it has not forecast, that the algorithm, the machine learning subsystem has not been able to concoct, to see, to extrapolate, then we are really dire straits. So how do we solve that? In my opinion, still, we have to go back to hardware. You know, I'm a kind of in between hardware and software, but I believe that hardware has been, how to say, downplayed too much, and that it should be a more important topic to look at. Why is that? Because I think that the combination of the sensors and actuators, when we are really in trouble, they should come in and stop the car, right? Instead of letting AI to decide what to do. Say, wait a minute, I am going to take over and I'm going to stop no matter what, because this is a dangerous situation, for example. This is just an example. And so, as I said, security, in my opinion, is going to make it or break it. So, okay, I saw. Okay, a comment by Ilor Horvitz. In fact, is you missed DEC, digital equipment, as one of big. In fact, I should have, because DEC actually was the company that funded most of the work that we were doing at Berkeley in CAD, believe it or not. Now, and it had a very good, I mean, I used to go there every year and give a class for 1 month class with my graduate students about placer route and, you know, and especially logic synthesis. And several of the managers, like for example, Antun Domic, who is a high-level manager of Synopsys, was the head of all the silicon design at Synopsys, was at Digital Equipment. So, and they had at the time when they were sponsoring so generously our research, they had the Alpha chip that was a very complex chip, was the most complex chip and most performing microprocessor. It was really a pearl of the design. And, you know, the unfortunate thing is that they failed to see the market developing, and, you know, it's so sad to see them gone. But same token, Bell Labs is also gone, basically. And so these two really important companies disappearing is really sad. And this calls to that thing that you have to be able to realize what you know, what is around you. You cannot pretend that if you are good, you are going to stay good forever. Now, I remember I forgot to answer one of the questions that was asked before. Is about, you know, the fact that the yield and so on, and we have to deal with components that are unreliable by themselves. Fine, right. This is definitely the case, but I was talking about the yield, about the function that the chip has to realize. So if I have a very large chip, there may be so many defects that I may not be able to correct them from a functional point of view, and that's what worries me. We were forecasting this situation like 10 years ago in a combination of industry and DARPA program, and we had this task of trying to build a reliable system out of unreliable components. And we went to a point, but then the extremely interesting thing is that, for example, Intel was able to get yield that yield meaning good transistors at such low dimension that we didn't need to apply the techniques that I was talking about before. If we think about 1 nanometer, maybe we will be able to deploy this algorithm. But, remember what I said about quantum computing. So to realize a real qubit is a pain in the neck because qubits are unstable. They are, they have to be maintained in a particular state and this and that and so on. And the trick that this company that I am so fond of has invented, quote unquote, is to make a real strong qubit out of a number of faulty qubits. And so that is, in my opinion, is a beautiful piece of work. But is related to what I was talking about before, because it doesn't have to be quantum computer. It can be a standard chip if you have an unreliable component. How do you build a level of abstraction where you can claim that you are perfect? Well, unfortunately, I think that when we really go to the deep end of the physics domain, then you really are obtaining at the functional level a system that maybe have been realized with a technology which is much less demanding and where we can have a much better component. So it's a very important trade-off between going down to lower and lower dimension versus what you can get at higher dimension. Then you have to compare the system, not the technology itself. Okay, so I see redundancy in the sense of 2 independent modalities can dramatically reduce the security problem, especially when it comes to fooling machine learning, right? Yes, so that's definitely the case. So if you, it's more of a, is a redundancy at a different level than what we are used to think, because redundancy, if you have 2 parallel paths, if one breaks, the other one keeps on working. But it's a redundancy at all the levels. So you can think about redundancy at the higher level of abstraction, where in order to achieve statistical independence, which is the key, I mean, otherwise we don't gain anything. You have to reach statistical independence, which means that you give to 2 different teams the goal of solving a problem, and they have to develop software completely independently. And then you have this property that p square tends to 0 if p is small, right? So
it can also be 2 different sensors, like in the example of the
absolutely
machine learning. If you had a different thing, it would recognize that this is not a bird.
Yes, well, easily. yes, but that's my point about hardware. And so the point is that you cannot just rely upon images, right? So for example, when I said you have to go down to hardware, right? Because at some point you have to realize that you are in a tough situation. I was thinking about, in a car, I would like to have, as they do, but I would like to have a radar. I would like to have a camera or multiple cameras, and I would like to have a LiDAR. So the combination of these, because then I'm much more safe in terms of being able to recognize something, but also to stop the algorithm, right? And say, wait a minute, you are not telling me to do the right thing. So I totally agree that redundancy at the sensor level is also very important, extremely important. And that is what we call sensor fusion, right? how you fuse the information that comes from different sensors. But you have to be very careful architecturally, because one of the sensors may be off, right? May be broken. And so you have to have also a way of detecting if something is unreliable, it went berserk, right? Because otherwise you run the risk of believing the berserk component rather than the right one. And so that's all. So if we assume that all the components are good, then sensor fusion is beautiful, because you have all the information you want. The more information, the better decision you can make. But you also have to solve the problem of detecting if something is broken. So for example, when we go in space, people use triple redundancy and a voting scheme, right? So if two guys say this is true and the other guy says it's wrong, then that guy is broken and the two guys are right. In general, it is a better solution, but it's not necessarily the correct one, right? So I can imagine a situation where the poor lonely guy was right and the two other guys were wrong. But you know, we go off on a all kind of discussion here that may not be germane to the situation. By the way, thank you. Very interesting questions. I really like them. Any other questions?
If not, Alberto, thank you very much. And
thank you for your
next
attention.
Time to have you here and not just via Zoom.
Yes, absolutely. I'd love to come back to Technion. I've been there a couple of times. And last time was about, maybe 10 years ago. So it's time to come back.
So hopefully after the vaccine.
Yes, indeed. Hopefully after the vaccine. Indeed.
Thank you.
Thank you. Goodbye to all.